Hello students, welcome to Legacy IAS Academy. In today's video, we are going to discuss about the East Reactor of China that made the news headline recently because of its contribution in the possibility of generating energy by the method of nuclear fusion. So what we can call as the China's East Reactor keeps the fire of magnetic fusion burning because of the recent breakthrough, recent development. Now, recent breakthrough that we are talking about is witnessed in the experimental nuclear fusion reactor, where for the first time, not only in China but in the entire world, the reactor was able to maintain its operational state for the longest duration of over 400 seconds, that is roughly 17 minutes. Now we have to keep in mind that reactor still has not produced any kind of electricity. It did not even carry out a fusion reaction, but the ability of the reactor to maintain the materials in the state of plasma is something that we can see is a beginning of or a big leap in the sphere of nuclear fusion energy generation. However, the reactor managed to maintain plasma in a steady state of confinement for a long time, longer than it had previously been possible by any reactors in any part of the world. Now, before going further, let us try to understand what do we mean by the term nuclear fusion. Now, we know that already many countries of the world, including India, have been successfully generating nuclear energy through the method of nuclear fission. Now, in the case of fission, it is a larger, we can say, isotope of an element that dissociates into two smaller or lighter atoms or lighter we can say elements, and in the process a huge amount of energy generated. On the other hand, in nuclear fusion, as clear from the term itself, we have the fusion of two lighter nuclei such as tritium, which is isotope of hydrogen, and deuterium, which is another isotope of hydrogen. This fusion results in development of helium, and extra neutron is then ejected, and also a huge amount of energy is generated here. For example, the amount of energy that is generated by deuterium-tritium reaction can be as high as 17.6 mega electron volt. Now, this is the energy, or this is the energy process, the fusion process that keeps burning our stars as well, including the sun. If you talk about the core of the sun, which is where nuclear fusion occur, there the temperature is as high as 15 million degrees Celsius. So that is the kind of temperature, the energy which can be generated by nuclear fusion process. Now, the problem that the world is facing in generating nuclear fusion energy is twofold. First problem is obviously the energy required. As we know that the fusion of two lighter atoms, and more precisely the fusion of two protons, can only happen if a very large amount of energy is supplied for this reaction. Even many scientists have claimed that temperature should reach at least 100 million degrees Celsius, and not only reach, this temperature should be able to maintain throughout the process of reaction. Then only successfully we can generate energy by nuclear fusion. Second problem is that there is a lack of tritium, because nuclear fusion can happen between two deuterium or two deuteriums, or between one deuterium and one tritium. The advantage of tritium is that deuterium fusion reaction requires a much more higher temperature than deuterium tritium fusion, and we are having problem of supplying energy. So for us, it is better to this what you can say facilitate deuterium tritium fusion. But here is the problem: deuterium is something that is found in abundant amount in the seawater, but there is no natural deposits of tritium, and it is very hard to produce. Even today, at the global scale, a very small amount of tritium is produced as a byproduct in the heavy water fission reactor, and these reactors currently are operational in few countries such as Canada, India, and South Korea. So first of all, even if you are able to become successful in producing such a huge amount of temperature, we need to ensure that we have a sufficient amount or volume of tritium as well. Now, second, if we try to understand more detail about the temperature problem, why such a huge temperature energy is required for nuclear fusion to occur, the reason is because for two nuclei to fuse, there are two things that need to happen. First of all, as we know, if you again look at this particular diagram, what happens in the nuclear fusion? You have a deuterium. Deuterium is an isotope of hydrogen having one proton and one neutron. Similarly, tritium is having two neutron and one proton. So for fusion to occur, what we need these protons and protons to come very close to each other. And we know that since these are both positively charged, they will repel each other. So that is why we need a huge amount of energy so that the forces of repulsion can be overcome in the protons. And if you supply such a huge amount of energy, we can see the two protons and the three neutrons then come together very close to each other, resulting in the formation of helium, which is made up of 2 protons and 2 neutrons. One extra neutron is separated, and as a byproduct, a heavy or huge amount of energy is produced. So that is why we require a very high amount of temperature. Also, as I told you that the protons and neutrons need to come together. Now, how close they should come together? The answer is it is 1 femtometer, which is a very small distance, even smaller than an atom of carbon, 1/4 of the atom of carbon, we can say. Now, the reason why they should come so close to each other, because then only they will be able to bond with each other with a strong nuclear force. Now, you will ask that what is the reason behind the generation of such huge amount of energy in nuclear fusion? The reason is that we talk about the nuclear forces. These are considered as the strongest fundamental force in the nature, and it is responsible for keeping protons and neutrons together in the nuclei of atoms. And it is this process of fusion that generates a huge volume of energy. Now, the question comes that in what kind of reactor we can facilitate such kind of fusion. So, there are several reactors that have been designed through the entire we can say history, but the most common reactor and the most successful one where nuclear fusion can be possible is what we call as a Tokamak reactor. So the Tokamak reactor is something that looks like kind of, we can call as a kind of solenoidal design, and inside this vessel it like basically act like a magnetic cage, and inside the vessel you have a deuterium gas that is exposed to a very high temperature of 20 million degrees Celsius, and it is at this temperature matter do not remain in the gaseous phase, they convert into what we refer as the fourth phase of matter, which is plasma phase. So the charged particles are then stripped from their respective atoms here at such a high temperature, and these charged particles are then floating freely. You can imagine that you have the protons that are freely floating in the entire Tokamak reactor. Now also these entire charged particles material are confined using electromagnets. Electromagnets are basically is when you pass electric current through material, it will start to produce magnetic field. So higher or stronger the electric current, stronger will be the magnetic field. So you need a very high magnetic field, extremely high magnetic field, to ensure that these materials are confined, these charged particles are confined within the reactor. Now, other thing that is used here as well is what we can refer as a superconducting wire. Superconducting wire means such kind of wire which carry electric current with zero resistance. So there is no loss of electric current, and this can happen if you are cooling a certain material to a very low temperature. So when you're cooling certain material to a very low temperature, they can become superconductor, and the cooling process here is achieved by coating and blanketing the material with liquid nitrogen or helium. So overall, what we can understand in the Tokamak, you have two major we can say activities or the process. One is the magnetic confinement, and second is the superconducting wire and electromagnet to produce the magnetic field. Now, as far as the yeast reactor is concerned, there are two magnetic field that is passed through this particular reactor. One magnetic field that is called as a toroidal reactor, toroidal magnetic field. Another is called as the poloidal magnetic field. So these two magnetic fields are then produced by the superconducting electromagnet that is structured around this particular Tokamak. As I told you, this is how the design of Tokamak look like, and currently the yeast reactor of China is the only Tokamak in the world having the features that allow the movement or passage of both toroidal and the poloidal magnetic field. If we talk about the toroidal magnetic field, these are the magnetic field that is being passed through or around this particular structure, core of the reactor, while the poloidal magnetic field passes through the center of this particular Tokamak. So that is the major difference between both. Now together they keep the particles within from drifting into the vessel's walls and collapsing the plasma. So first the plasma state should be maintained for sufficiently high period of time, and it is due to this they start moving in, we talk about the charged particles, they start moving in a spiral pattern throughout the vessel, and if they are moving in a spiral pattern at such a high speed, there is a possibility that two protons then collide with each other, they can come close to each other, they fuse, and then the nuclear fusion will happen and the energy can be generated. So the reason behind the design of this reactor is like this, a spiral design is like this, is because it will facilitate the fusion of two protons that are moving in a state of plasma. Now, as I told you before as well, that if we talk about the current status, yeast reactor has not been able to produce electricity, but its breakthrough is considered very significant because it will be a test bed reactor for the ITER, that is the International Thermonuclear Experimental Reactor, where many countries of the world if talk about including India as well as European Union working together to develop such pilot scale reactor where nuclear fusion can produce electricity, then it can be then further we can say the pilot project can be further amplified and actual reactor can be established through which nuclear fusion can become reality. Now, in fact, if we talk about this reactor, it is yet to reach a milestone called ignition. Ignition is the place where it does not produce, where you have the sufficient amount of heat, where the reaction becomes self this sustaining in nature. So that is still a long way ahead or long road ahead from now. Now, it is not only that the Tokamak kind of designs that we talk about can produce nuclear fusion, there are some other alternatives as well. And one of the alternative to the Tokamak is something that is called as accelerator. If you look at the picture here, it will be clear that Tokamak is a kind of donut shaped cylinder, donut shaped vessel. On the other hand, stellarator is something that is a twisting kind of shape we can give it. The benefit of stellarator is that it does not need a poloidal magnetic field to achieve a twisting magnetic field inside the vessel. Rather, in the case of a stellarator, the twisting of magnetic field is achieved by designing of external magnet itself, and thus instead it achieves the desired field configuration using a more complicated architecture of external magnet. Now, this is again also one alternative. The basic principle, however, behind both, that is the Tokamak and stellarator, will remain same. The plasma state will have to be achieved. The proton will have to move at a very fast speed in the spiral fashion, and that is when they can collide and fuse together. The other alternative on which a lot of work has been conducted and done is the use of laser beams. However, in the initial phase, the laser inertial fusion energy, the LIFE project, was cancelled in 2013 after it became clear that it could not achieve ignition. But in the same institute, that is the National Ignition Facility in the United States, another research has achieved this milestone in 2022. In this particular case, a system of 192 high power lasers were used to deliver high temperature by producing energy. These 192 high power lasers deliver collectively 2.05 megajoules of energy, and this energy was concentrated toward a smaller cylindrical capsule at the center of the room. And if you talk about this small cylindrical capsule, within this capsule was a thin cell that was made up of polymer, inside which you have the deuterium and tritium atoms were placed in a frozen or gaseous state. So you can understand that the entire 192 high power lasers which are producing such a huge amount of energy, their energy is concentrated over this thin cell of polymer. That means they are trying to excite both deuterium and tritium to such a state where the proton-proton repulsive forces can be overcome, and then both atoms can join together, both elements can join together, forming helium and releasing the huge amount of energy. So apart from Tokamak design, this is something that also seems very promising, and maybe in the near future we might see the success of the laser based nuclear fusion at the pilot scale at least. But still, we have a long way to go before we are able to develop a commercial scale nuclear fusion reactor. Till then, we have to be, we can say we have to do away with the nuclear fission itself, and that is where the government of India is currently also trying to expand its capacity. So that is all about this particular video. I hope you got the idea behind the process, the phenomena of nuclear fusion, and why the current development in the Chinese reactor, China's East reactor to be more precise, is significant not only for the China but for the entire world as well. So if you like the video, please hit the like button, share it with your fellow aspirants, as well as subscribe to our channel for more such content. Thank you very much.